So in this part of the lecture, I'm going to discuss the discrete Fourier transform. So I'm going to let the vector x equal vector x0 is the first entry, x1 all the way down to x sub n minus 1. So there are n entries. And I'm also going to let omega equal e to the minus 2 pi I divided by n. And so the definition of the discrete Fourier transform is basically multiplication by a certain matrix and this vector x. So y, which is going to equal, it's going to have components y0, y1 to y sub n minus 1. It is going to equal 1 over the square root of n times the matrix. Consisting of omega to the 0 as each entry in the first row. The next row, omega to the 0, then an omega to the 1, omega squared, so on and so forth until omega to the n minus 1. And hopefully you can see the pattern, and if the matrix isn't clear to you, you can see what the matrix looks like in the book. Basically, each row just raises the power of omega in a certain fashion. And so this matrix here that is multiplying the vector x, including the factor 1 over root n, is, I'm going to label as f sub n, and this is the Fourier matrix. Okay, so really it's a matrix made up of complex numbers, and you can see that it is a symmetric matrix and how it's defined. There's also a nice shorthand notation for this discrete Fourier transform, which is that y sub k, the kth entry of our vector y, is equal to 1 over the square root of n times a summation from j equals 0 to n minus 1 x sub j omega to the jk. So this is a nice shorthand notation. It's certainly better to view this as a matrix vector product, as you see above this shorthand notation. We can also define the inverse Fourier transform. And this is the inverse discrete Fourier transform. So, and I'm just going to abbreviate it, the inverse DFT, and the discrete Fourier transform is usually abbreviated as the DFT. So the inverse discrete Fourier transform goes by the following matrix. So as you can see, the inverse discrete Fourier transform is basically similar to the discrete Fourier transform, except you see that the exponents of omega have all been negated. And so let's take a look at this, what this negation of the exponent means. So if you consider omega e to the I theta, let's consider omega equals e to the I theta, and consider its complex conjugate. So omega, if we use Euler's formula, is equal to cosine theta plus I sine theta. Well, the conjugate of omega is equal to the cosine of theta, of course, minus I sine theta. We just negate the imaginary component. And now what is this in relation to omega in its polar representation? Well, notice that this is equal to cosine of minus theta, since cosine is an even function, and then minus I, or I'm sorry, it's actually plus I sine of minus theta, since sine is an odd function. And so what does this equal? It equals e to the minus I theta. Okay. So basically, in conjugating any complex number, you are basically negating the angle that is made with the unit circle if we're dealing with complex numbers on the unit circle, but that can be generalized in the sense that if you have a complex number and in its polar representation the angle is theta, the conjugate will have the same polar representation with an angle of minus theta. Okay, and so this is just the result for complex numbers on the unit circle, but this generalizes to all complex numbers. So what does this result mean? It means that if we take omega and raise omega to the minus j, this equals the conjugate of omega raised to the j power. Okay? And so, in regard to the inverse discrete Fourier transform, it is equal to the conjugate of the Fourier matrix. And so now some definitions. Well, it turns out that the matrix is unitary if and only if the conjugate transpose of the matrix it's the inverse of the matrix. So, and this would be written in this notation. So the F sub n bar transpose is the complex conjugate transpose. So basically, not only do we transpose, we also take complex conjugates. And F sub n is unitary if this product is the inverse, which means that the inverse of F sub n is its conjugate complex transpose. This is the analogous to an orthogonal matrix for real matrices. Right, and so I've mentioned this previously, that the magnitude or the modulus of a complex number is basically a square root of a sum of squares. And so we can write that as, so if we have a complex number, call it v, so it is equal to the square root of the conjugate transpose of v times v, and then taking the square root of that. So this is the definition of the modulus, and so if we consider our discrete Fourier transform, and if we look at the modulus of y, of our vector y, and remember our vector y has entries that are in general complex numbers. So this is equal to, well, it's the magnitude of f times x, which is equal to the square root of, in parentheses, the conjugate of f times the conjugate of x, and then transpose of that times fx and then when we take the transpose of a product, it is a product of transposes in the reverse order, and so that would be written in this manner. It'd be the conjugate of x transpose, the conjugate of f transpose, times f, and then times x. And so now if we group the f conjugate transpose in f, what is that? Of course, this part here is equal to I, and so that we get this is equal to, well, the magnitude of x. And so what does this mean? It means that the DFT, the discrete Fourier transform, does not change magnitudes. And this is something that's important in scientific computation. And that is not changing magnitudes. So an example of computing a discrete Fourier transform, let's find discrete Fourier transform of x equal to the vector 0, -1, 0, 1, and I'm going to write it as a row vector and then transpose. So this is a vector with 4 entries, and so our Fourier matrix is a 4x4 matrix, and so our product y is equal to 1 over the square root of n, which of course is 1 over the square root of 4, and times the matrix. So first I'm going to write it out in terms of omegas. We have an omega to the 0, omega to the 0, omega to the 0, omega to the 0 in the first row, omega to the 0, omega to the 1, omega squared, and omega cubed in the second row, omega to the 0, omega squared, omega to the 4th, omega to the 6th in the third row, omega to the 0, omega cubed, omega to the 6th, and omega to the 9th in the fourth row. All of this times our vector 0, -1, 0, 1. And of course omega to the 0 is simply 1, so we have a bunch of 1s across the first row. 1s down the first column, okay? And now if we go out across the second row, omega to the 1 is, in this case, it's omega to the minus pi I over 2, all right, which puts us at, on the imaginary axis at I. And of course we're going in the clockwise direction, so we're at minus I. And then if we keep going in the clockwise direction 90 degrees, omega squared, we get omega squared, which is -1. And then if we go another 90 degrees, which would be omega cubed, we are now on the imaginary axis at I. Okay. And so if we go to the third row, omega squared, we just computed that it's -1. Omega to the 4th power is now, we're back to 1 on the imaginary axis, and omega to the 6th power is now similar to omega squared, which is -1. And you can notice the symmetry as well. We can take advantage of the symmetry. So this entry is I, this entry is -1, this entry is minus I. So now we're multiplying by the vector 0, -1, 0, and 1. And if we do this multiplication, this equals 1/2 times the vector. Alright, so we get a 0 in the first entry. In the next entry we get 2I. The third entry is 0, and the fourth entry looks like it's -2I. So if we distribute the 1/2, we get the vector 0, I, 0, minus I.